first speaker is David Benisty, who is going to tell us about the cosmological constant in the local universe.
Okay, so thank you very much. It's a great pleasure. Thank you for the invitation. So I'm going to speak today about something that usually the cosmology community doesn't do, but from some reason, people not aware of that. So let me just give you the statement of the talk. It is possible to detect the cosmological constant not from cosmology. Okay? It is possible to detect the cosmological constant from nearby galaxies such as Milky Way and Andromeda. And these are not the only galaxies in the local universe. There are much more that actually Lambda changes the whole motion. Okay? And many astronomers were surprised to hear that, but today I'm going to convince you this is actually correct. But in order to do that, there is a specific method how to do, so I'm going to just like to sketch the idea. And besides this one statement also that I would love to give you, it is possible to see whenever lambda or lambda CDM, it means that you have a cold dark matter in the early universe and the cosmological constant at the end is actually changing the mass of Milky Way and Andromeda. So it is possible to know what is the correct model for the history. Okay? So these both statements you are going to see today. So first of all, the H0 tension is not only H0 tension. This is actually the cosmological constant tension. Right? When you write the term R minus 2 lambda or something like that, you get from cosmology two independent values for the cosmological constant. So as you can see, this is in the blue area, this is the value that you get from Planck, and this is the value that you get from Hughes fit. Because the cosmological constant is coupled to the Hubble constant square, but also to omega lambda. So it means that actually the Hubble tension, this is not only just like the expansion rate currently, this is actually a different fundamental constant that appears in our equation. Okay? So this is a much more fundamental problem. So where can we see this detection of cosmological constant directly? Not just like, that I have to assume something about the expansion and so on, and then to derive lambda. So in order to know that, first let's go to the basics. So the basics is the geodesic equation, and then if you write the Newtonian force, the low energy limit for the Newtonian force, you get the Newtonian part, and then you get some expansion, some repulsion force that comes from the cosmological constant itself. Now, in the literature, the area where the cosmological constant repulsion force and the Newtonian force that cancel in each other, it's called the acceleration surface, or the zero acceleration. Now, this is the value. Just like take the first equation, equals to 0, and then this is the solution. Now, if you insert, and this is kind of like the guideline that we'll see in a bit, if you insert the mass of the local group, the mass of Andromeda galaxy more or less is 10 to the power of 12 solar masses. The mass of Andromeda, it's 1.5, 10 to the power of 12 solar masses. If you insert these numbers inside, you get that the distance where the repulsion force of lambda is actually 2 megaparsec. The distance where the domination of the cosmological constant is 2 times the distance in between Milky Way and Andromeda. Okay? So this is why actually the cosmological constant is changing the whole motion of Milky Way and Andromeda. So just like to give you another numbers. Okay? So this is the Milky Way, this is Andromeda. We have also the Large Magellanic Cloud, which is really close by. Okay? And we have a lot of small dwarf galaxies. Now, the distance in between Milky Way and Andromeda, it's 0.77 megaparsec. Okay, so very close to 1. And the acceleration surface, so it means where the repulsion force of lambda is actually canceling, it actually creates some sphere around it, which is about 2 megaparsec, or 1.5. So it means 2 times the distance. So in other words, the cosmological constant is dominating very close by from the equation of motion, just very close by to the Milky Way and Andromeda. So any motion that you have to take into account in these rates, you have to take lambda as well in two-body problem. So this is just like the schematic scale that you can see. For instance, this is the Milky Way and Andromeda. These are the streamlines, and these are the dwarf galaxies around it with axially symmetric behavior. And besides this, it is possible also to reconstruct for the close-by galaxies in the local universe. So here you see the local group. Here you see Centaurus and M83, and you see other groups, the giant galaxies, they have more or less the same mass. And all of the circles that you see around here, these are the areas where the cosmological constant is canceling the Newtonian attraction inside. Now, which assumption I took into account here? I took the dwarf galaxies just as point particles, okay? So this is why, I mean, again, if you want to analyze the motion for all of these galaxies, lambda is not negligible. And by the way, cosmic flow, Brentoli et al., always take the Newtonian force. So what I'm saying, this is not fully correct to do so. I mean, there is some correction that you have to take into account. Now, what I want to speak to you today, this is actually also that the full history of Milky Way and Andromeda is very sensitive whenever you take just lambda or the full lambda CDM. Okay, so what do I mean by lambda or lambda CDM? So, okay, so we have the Einstein theory of gravity, r plus lambda, but then if you want like to solve the equation of motion, so here by equation of motion I mean for the Milky Way and Andromeda, okay? So we can solve the spherical symmetric behaviors. So this is the spherical behavior, and this is the equation of motion that you get if you just assume spherically symmetric behavior. So you just get a repulsion force of lambda. This is what you saw before. However, if I'm assuming what's called the McVitie metric, the McVitie metric assumes that you have two galaxies or 2 point particles in that case, in that model, but then the whole space-time is expanding. So you have a spherical behavior, you have a potential over some expanding background. When you take this metric, you get, instead of lambda, you get a double dot over a. A is the scale factor of the universe. Now, as you can see, in later times, this is asymptotically constant, dark energy domination. But in earlier times, because we have a matter domination universe, actually we get an attractive force, not a repulsion force. Okay? So what I'm going to show you that these two models are actually predicting different local group masses. And for your question, because these are just like 2 point particles galaxies, we also calibrate by simulations. Okay, so we take also like this effect into account. So the first one who tried to model the local group as a two-body problem was Donald Lindell-Bell, okay? But it was from the perspective of two bodies. So now you assume that you have just like two bodies as the Milky Way and Andromeda, and they are in their infall, okay? So in his assumption, they started from the Big Bang, so for very small separation, and then they expand because of the first expansion of the universe, and then until the distance that we see today. So I mean, you can see that, for instance, this schematic plot here. So this is today, Andromeda is approaching us, and then this is the full motion using the timing argument. Okay, and again, this assumption only for point particles. We have to take some corrections into account. Now, the strange thing in this kind of like assumption, I mean, we can infer the mass because we have the final location and the final velocities, and we have also the initial conditions. So if we solve that, we can actually predict the local group mass. But what is the strange thing? That if I'm including the cosmological constant, so just lambda in the equation of motion, I'm getting 10% higher mass. Okay, so the mass is actually become higher. But if I'm including the lambda CDM, a double dot over a, then we get actually lower mass. Now, why is that? If we have constantly, for the whole history of the universe, a repulsion force of lambda, we have to compensate with that with higher mass. This is why the m is actually larger. But if we have a double dot over a, so it means that in earlier times, this is an attractive force, so we don't have to have so much mass, okay? So it's actually lower. So I mean, here you can see that the different masses, I mean, for the Newtonian timing argument, this is about 4. With lambda, the first one who discovered it was Patrick, Jennifer Lahav, and Yehuda Hoffman. It's increasing the mass to about 5. But then if you use the a double dot over a, this is crosses the 4 or sometimes even 3. Now, just like to tell you, this is like a small detail, but I mean, all of the details that are also like in CosmoVerse talk that I gave, it is like on YouTube, so you can see like the full two-body problem solution, how it actually enters. The lambda, the cosmological constant, it behaves as a critical period in binary motion. So it means that if you have a binary galaxies or binary system that has a period of 35 gigayears, the lambda is going to change the whole motion. Okay? So this dimensionless parameter, this is just the lambda force over the Newtonian force. Okay? So this dimensionless parameter always appears in the solution. It doesn't matter if you do a perturbation, a full solution, and so on and so on. Always this ratio always appears. And this ratio is the Keplerian period over the 35 gigayears. The 35 come from lambda value. Now, the Keplerian period of Milky Way and Andromeda is about 17. 17 over 35, it's about half. Half square, quarter. Okay, so this is why the cosmological constant is dominating also the two-body problem in this context. Now, what is the problem? We're taking a look on Milky Way and Andromeda as binary motion. I mean, these are two galaxies. We have a lot of halos. We have a lot of other noises. So what is the possibility to actually compensate for that? We can do a simulation calibration. So in this n-body simulation, they throw away inside a lot of matter, okay? And then they assume some interaction in between the matter that there is in the simulation, okay? And then you have structures that emerge inside. Now, after you run this simulation for a lot of time, you can distinguish or you can see a lot of pairs, galaxy pairs inside it, or halo pairs. And you call this local groups. So now, from the simulation, we have a lot of pairs inside the simulation themselves. So we know the separation of all of these galaxies inside the simulation, we know the velocities, and we know the masses from the simulation. So it is possible to compare the prediction of the timing argument from the analytical solution to the n-body simulation. So this is what you see in the right-hand side plot. Here you see the analytical solution or the numerical solution from the timing argument. Again, timing argument, it means two-body problem versus the virialized mass. So you see that more or less this is actually agrees, but you have some bias that you have to take into account. Okay? So how you can calibrate by simulation? Anytime that you have galaxy pair or some pair from the data, okay, the separation of Milky Way and Andromeda is this value, the velocity is this value, then you calculate the timing argument mass, but then you try to select or to see from the simulation which is the closest pair, or 10 pairs in this case. And then you can calibrate what is going to be the corrected mass by the simulation. Okay? So, just like to tell you, and there is also a different effect which has to be taken into account. This is the Large Magellanic Cloud because this is changing the center of mass, but I'm not going to enter for all of these details. But, as you can see again, the Newtonian timing argument gives us about 4.5. With lambda, it even crosses 5. And again, this is biased high because the total mass of Milky Way and Andromeda, it's close to 3. But then, if you take A double dot over A with the simulation calibration, you see that the masses are crossing to the area, this is in red, which is the total mass of Milky Way and Andromeda from independent estimations. Now, when we include also the LMC effect, which changes the center of mass, you see that the mass sits almost perfectly on the range. Okay? So what does this mean? I mean, lambda CDM, the full history of the universe, I mean, if you just assume the two-body problem with the simulation calibration, the full lambda CDM predicts for you a mass which is compatible with completely independent estimations of the Milky Way and Andromeda. Okay? So is that sensitive? So other masses in the literature, just like to give you an idea. Here, this is by the virial theorem. If you assume that you have Milky Way and Andromeda, all of the dwarf galaxies around it, they are obeying the virial theorem, it is possible to infer this mass, 2.6. Hubble flow, this is a fit for the Hubble law, but also with the Newtonian attraction. So this is what you see in this plot. You see here there is kind of a line, but on closer area, this is the Newtonian attraction. Okay? So if you fit that equation, you get 2.5 for the mass. And this is only using the simulation with Gaussian processes, or some ANN method. But with all of this estimation, these are the masses that you see here, they are falling into my final estimation. Okay? So it means the total mass, if you take the total mass, Milky Way is about 1, Andromeda it's about 1.5, the total mass is actually compatible with this independent estimation. Now, is it possible to constrain lambda from the local group dynamics? The answer is definitely yes. Because the cosmological constant is the repulsion force. So as long as you have stronger repulsion force, the total mass of the local group should be higher. I mean, you can see that in that plot. See? This is the numerical dependence. On the other hand, we have independent estimation for the local group mass. Is this value here. So after I did the complete Monte Carlo, I got like two different values. I mean, you say like the mean and the variance. But then it means, from the mean plus the variance, that the upper bound on lambda is about 8 times the value from Planck. But again, this is agnostically only based on the local group history. We can have lambda which is up to 8 times. Okay? So obviously if we'll add other systems, or if we add also the dwarf galaxy analysis inside, we can actually have an independent detection for the cosmological constant effect, or the Hubble constant in this case. So, to summarize, first of all, I mean, in cosmic flow, I mean, all of the estimations in the local universe, usually people take into account the Newtonian force, but also the cosmological constant has to be taken into account, because the lambda is actually what sets these groups to be bounded from infinity. So I mean, after a long time where they have obeying the Virel theorem, they get some boundary around it. And then all of the galaxies are kind of like collapsing inside. So it means this is by the way, set by lambda. If you insert lambda inside, you can see that from the Virel theorem. And if you include the full history of lambda CDM, also you can get a mass which is compatible with the independent measurements of Milky Way and Andromeda. And with that kind of like correlation between the mass and the local and the cosmological constant repulsion force, it is possible to estimate upper bound of lambda. Okay? So I mean, just like to tell you, I mean that this is kind of like the thing that I'm pushing now in my research. I mean, different systems or also the dwarf galaxies analysis inside will insert more information and will give a detection, not just like an upper bound for the cosmological constant. So this is my statement for today. Thank you very much.
Yes, time for questions.
Nice presentation, but I'm disturbed. I don't know. It seems that you take into account some Newtonian gravity on one side, visualize objects on the other side, and perhaps the GR on the third side, but I'm not sure. Can you give me some clue to understand your point?
I mean, in the local universe, all of the velocities that we detect today, I mean, they are fully Newtonian regime. Okay? So we don't have any post-Newtonian effects or something like this. I mean, this is not the energy limit that we need to take into account. Okay? Obviously, in the past universe, we don't know. Okay? I mean, we can base it on simulation or whatever, but I mean...
Lambda is not Newtonian. There is no lambda in the Newtonian equation.
There is no lambda in the Newtonian equation, but in the low energy limit, there is lambda. No, if you take the potential to be in the low energy limit, the potential phi, if you include r plus lambda, and then you assume that phi is very low, you get lambda correction into account, yes?
How we can detect it in the lab? What is it? Source we know, we can measure forces.
Do we have cosmological constant in the universe? I'm asking the question. Do we have lambda? So we need to see it in the late universe as well. This is what I'm saying. And if this exists, also we need to see these effects in the local universe.
Can we see it in our lab?
No, but there is a reason why not. Because the curvature is not close enough. This is what I'm saying. There is an energy scale which is actually compatible with that. And the energy scale in the local group is actually touching in the lambda regime. I mean also, do you know the Kretschmann scalar, the curvature scalar? If you put the curvature scalar, you get some contribution from the Newtonian part and from the lambda part. But you will see that lambda is compatible with the mass over radius, over radii. So it means that this is the compatible curvature. It's not only just like an assumption. Okay? The Kretschmann scalar or other scalars, if you put r plus lambda, you will get some dependence on the mass and the radii, and also by lambda. And then you'll see that these two parts, they are not negligible. They are really close to each other. Okay? Is it answering your question?
No, I don't understand how you have got, for example, visualized object with a lambda inside.
Oh, no. First of all, okay. So first of all, the analysis that I've done is related to the two-body problem. Okay? This is not, I didn't assume a virialization with the Milky Way and Andromeda. They're in full. The virialization with the dwarf galaxies around it. Okay? Now, the virial theorem with lambda, I mean, this is like studied in the literature a lot. I mean, it is basically, you can also do it for McVitie spacetime. You can do it also with lambda itself, okay? That the repulsion force of lambda is actually sets for you the boundary. I mean, you get like some repulsion, lambda r square, some potential, and then after a long time, when you integrate after a long time, you can get actually this boundary. Okay?
Thank you, David, for the interesting talk. I think it's a very nice idea, and probably will give interesting bounds. My question is, in the previous slide, you have two bands. One band is the orange and the other is the blue.
Yes.
Okay, the blue is clear that how can you obtain, but what are the assumptions hidden in constructing the orange-blue? I mean, shouldn't in the orange-blue also somehow enter also the cosmological constant?
Yes,
I mean, how do you put this constraint without taking into account the cosmological constant?
Oh, so I took into account the cosmological constant, but then so here you see the two models. You have A double dot over A, okay? The question, what is the background equation of motion? So A double dot over A, this is one part, or lambda, this is the another part. This is the red versus blue.
No, we can talk about the left.
Ah, this one? Yeah. Ah, okay. So I mean, in the left part, you have the equation of motion. So then you infer the mass by the timing argument with lambda, different values of lambda. And then you use the simulation calibration. What is the correction factor from the simulation itself? In order to probe the mass.
But shouldn't this have a dependence on lambda also? I mean, I think the orange...
No, this is independent calibration from the literature. So if you take like different masses from the literature, you get like this kind of like errors.
The literature doesn't take into account any lambda, so how can you trust it?
Ah, okay, so the assumption here, that's true. I mean, here there is an assumption that the mass of Milky Way and the mass of Andromeda, the total mass of them, this is going to be the mass of the local group in this kind of like branch. Now, there are other independent estimations, as you can see here, for instance, from the Hubble flow or from the virial theorem, yes, that they also got like the same mass, but from completely independent assumptions, or by assuming virialization, or the fit to the Hubble flow. Okay? So I mean, also you get like independent masses that are sitting inside this branch. But this is an assumption that
That's a crucial assumption that one has to be careful.
Yes, I totally agree. Yes.
Let's thank David again.